Swayam Prabha. Digital India. Educated India.
So, good morning, and we are talking about the conservation of linear momentum, basically on our way to deriving the Navier-Stokes equation, okay, the equation of momentum, which we will use to get the flow field in a liquid. So, we were looking at the Reynolds transport theorem, and we wanted to apply it for conservation of momentum, in which case the specific property was going to be the velocity. Okay. So, let us go back to the Reynolds transport theorem, and we are talking about conservation of momentum, and here eta is the velocity, that is the specific property, that is the intensive property which is independent of mass, and momentum per unit mass, that is velocity. Okay. So, now if I were to write the Reynolds transport theorem, I would get over the control volume of eta rho dV plus integral of the control surface of eta rho v dot dA equals d dt of NCM. Okay. And N here is capital N here is the momentum that we are talking about. So, basically what I have done is this is the momentum of the control mass. This is taking into account the fact that there is going to be fluid flowing across the control surface, because of which momentum can come in, go out. This is a net efflux, net rate of efflux. This is like the accumulation term. So, this is the accumulation term, and this is out minus in, and this is your generation term. Okay. So, all we have to do is put eta as equal to velocity, the velocity vector, because that is my specific property. Okay. And I can pull this derivative inside. I get d by dt of rho v dV plus this guy here is integral over the control surface of v rho v dot dA equals d by dt of NCM. Now, we want to convert this surface integral into a volume integral using the divergence theorem, and we do that, and we combine the two terms on the left hand side, and I am going to pull the, what justifies the taking the derivative inside is the fact that my control volume is fixed. Okay. It is not changing with time. So, I am going to pull this derivative inside, and when I use the divergence theorem, I would get divergence of rho v over the volume element, and the right hand side I said was going to be equal to the forces which are acting. Okay. These are the forces, because from Newton's law, okay, the rate of change of momentum of a material mass, okay, of a fixed mass of molecules that you are looking at, the rate of change of momentum of that is going to be given by the forces. Force equals rate of change of momentum. Okay. So, that is basically what the this is, and this I am going to divide into body force plus surface force. Okay. So, body force means it is going to be acting on every molecule, every material, particle in the control volume, like gravity. Gravity is going to act everywhere. Okay. And so, the most common body force that we encounter is the gravitational force. In addition to gravitational force, there can be other kinds of body forces. For example, if you have an electrically conducting liquid, if you apply an electric field, the electric field will act on all the ions which are present, okay, and that is going to be present uniformly in the body. So, that will contribute to a body force. If you have a magnetic field, that will also and if you have magnetic particles, that will also give rise to a body force. Okay. So, body force does not mean only gravitational force. I think that is what somebody was trying to ask me towards the end. Most common body force that we encounter is the gravitational force. Other body forces could be of electromagnetic origin, okay, and it depends upon whether that is important or not, because sometimes people put electric fields for certain applications. So, that is the field of electrohydrodynamics, magnetohydrodynamics. So, there are a lot of people working in those areas, but we are not going to focus on those right now. So, right now when I say body force, I only mean gravitational force, okay. So, most common body force is the gravitational force. Other forces could be of magnetic or electric origin. Okay. You can have a magnetic force, electric field, that can also give rise to body force. Okay. Other body forces. Okay. So, if you look at the body force, what I am going to do is I am going to write this for the entire control volume as rho g dV. Okay. That is your body force which is acting on the material mass. My control volume has material inside, molecules, particles inside, and at each point there can be variations in the density. So, therefore, I put the density here because it can vary with in the volume. G is going to be uniform, let us say, everywhere, that is G, and dV is your volume element. So, rho dV is your mass element and G is the acceleration due to gravity. So, this is the way I would write the body force coming due to gravity. Now, so you can see that this is already in the form of a volume integral. This is in the form of a volume integral, and this surface force that you are going to see is clearly going to be on the surface, is going to be in the form of a surface integral, okay. And that is something which we have to find out, and that will give me, and on the surface you will have the pressure acting, and that gives rise to your pressure term and the shear stresses acting, which will basically complete the Navier-Stokes equation. Typically, when you look at the Navier-Stokes equation, you will have these terms on the right hand side, okay. This is what is going to be on the right hand side, on the left hand side. On the right hand side, you will have the forces, okay. So, I have basically rewritten what I did last time with that shift. So, this is your also what is called the inertial terms. These terms here, these are the inertial terms that people talk about, and you have the forces there. So, before I start worrying about how to calculate the surface force, okay, and tell you how to do it, I want to go back a little bit and explain a few things about and set the background for calculating the surface force, okay, rather than just directly jump into calculation of the surface force. So, by way of background, I want to motivate it by telling you how do you calculate this. You know how to calculate the dot product of two vectors, okay. This is del dot rho VV. So, V is a vector and is happening 2 times VV. So, how do you calculate del dot rho VV? So, basically what I am going to do is talk about how to make these calculations, okay, which will be useful, and do it in a kind of a general setting, so that you can apply it to any problem, okay. So, we are going to talk about some vector operations, vector identities, vector calculations, okay. So, that and then after that we will talk about how to find the surface force, okay. So, rather than directly jump into calculation of the surface force, some basics of, shall we say, vector calculus, okay. That is what we are going to talk about, to set the background to find the surface force, okay. Now, typically you are used to a velocity vector u, okay. You would write it as, and right now we are talking mainly Cartesian coordinates x, y, z, okay. So, the velocity vector will have 3 components in x, y and z, right, and you would write this as ux ex plus uy ey plus uz ez, right. E are the unit vectors. So, ei is the unit vector in the direction I, and ui is the component of u in the I direction, okay. So, rather than write in terms of x, y, z, what I like to do is write this as u1 e1 plus u2 e2 plus u3 e3. I am saying e1, the first coordinate is x, second coordinate is y, third coordinate is z, okay. So, I mean same thing I have written, I have just replaced x with 1, y with 2. So, x is 1, y is 2 and z is 3, okay. That is my x is my first coordinate, y is my second coordinate, z is the third coordinate. Now, the advantage of this is I can write this as sigma ui ei, I going from 1 to 3, correct, okay. I am summing over I. So, I mean if I x, y, z, you can only sum over integers, you can sum over alphabets, okay. So, we are trying to come up with notations which can be used mathematically elegantly. So, rather than you do not say summing over a, b, c, d, how can you sum over a, b, c, d, you can sum over 1, 2, 3, okay. So, that is the thing. Similarly, v can be written as sigma, this is just a dummy index, Vj Ej. It does not matter, right. I mean j is also going to go from 1 to 3 and I is also going to go from 1 to 3. I can use I also, but for keeping things general, I am keeping them different. When it comes to finding the dot product of u dotted with v, okay. So, what would be the dot product? And remember E1, E2, E3 are orthogonal, they are perpendicular to each other. So, E1 dotted E2 is 0, E1 dotted E3 is 0, E1 dotted E1 is 1, okay. So, basically what I am saying is this is going to be sigma. Now before I do this, sigma ui vi, sigma ui ei dotted with sigma vj ej. Okay. Now we are going to write this as ui ei dotted with vj ej. I have dropped the summation sign, okay, and the reason for that is we are following what is called the Einstein's summation convention notation. What it says is, if in a particular term a particular index is repeated, then we are summing over that term, okay. In this term I is repeated, that means we are summing over I. In this term j is repeated, that means I am summing over j. I do not have to explicitly write the sigma sign, okay. So following Einstein's summation convention, if in a term an index is repeated, then we are summing over it, okay. So ui ei means I am summing over I, uj vj ej means I am summing over j, because j is repeated, I is repeated. Now what you know is ei dotted ej is equal to 0 if I is not equal to j and equals 1 if I equals j, right. If I is not equal to j, there are two different coordinates, because of orthogonality they are 0. So what can we do? We can write ei dotted with ej as delta ij, which is the Kronecker delta. So this is the Kronecker delta function, okay. So Kronecker delta function is nothing but delta ij. It is equal to 0 if I is not equal to j and is equal to 1 if I equal to j. So this is the Kronecker delta function, okay. That is the definition of Kronecker delta. So I am just saying ei dot ej is delta ij, okay. Now so when I come here, look at ei dot ej. Why did I keep these indices separately? Because I want to allow for all possible combinations of I and j. I will go from 1 to 3, okay. I get E1, E2, E3 here, j also will go from 1 to 3. If I keep the same thing here, then I am only looking at E1 and E1, E2 and E2, E3 and E3, okay. So you need to consider all possible combinations of I and j. So in order to consider all possible combinations of I and j, I am keeping different indices. If I keep the same index, what does it mean? If I take 1 here, I am forced to take 1 here, okay. So I do not want to do that, I want to keep it general. So that is the reason the indices are different. So clearly what is this going to be? Only if I is equal to j, this is going to contribute, okay. And so u dotted with v equals ui vi, because j has to be equal to I in order for it to be 1. Ei dot ej is equal to 1 if it is I is equal to j. If I is not equal to j, ei dot ej is 0. So only I equal to j is going to contribute, okay. So ui Vi is what I get. So look at that. If it's not clear, let me explain. This is U1 E1 plus U2 V2 E2 plus U3 E3 dotted with V1 E1 plus V2 E2 plus V3 E3. When I do the dot product, only E1 with E1 is contributing. E1 with E2 and E1 with E3 will be 0. Okay, E1 dot E2 is 0, E1 dot E3 is 0, only this one contributes. So this is equal to U1 V1, again U2 E2 dotted with E2 only contributes, E2 dotted E1, E2 dotted E3 is 0. Okay, that's how I got that. So now you go to the, so how do I use this thing to basically do my calculations? Okay, so for example, if you look at your equation of continuity, in equation of continuity, we have a term del dot u. Okay, divergence of u. And what is the del operator? I can write it as Ex d by dx plus Ey d by dy plus Ez d by dz. This is my del operator. It's a vector. Okay. Now what I'm going to do is, I'm going to, the three spatial coordinates x, y, z, I'm going to call them x1, x2, x3. Okay. X I'm going to call x1, y I'm going to call x2, and z I'm going to call x3. Okay. So this is basically going to be, I can write the del operator as Ei d by dxi. Again, I is repeated. That means it is summed over 3 times. Okay. So I have E1 d dx1, x1 is x, Ex d by dx, E2 d by dx2, that is Ey d by dy. Okay. So you just have to start thinking in terms of x1, x2, x3, not x, y, z. Because tomorrow x1, x2, x3 can be r theta z in cylindrical coordinates. It could be r theta phi in spherical coordinates. Okay. And E3 d by dx3, what is that? This is basically E1 d by dx1, E2 d by dx2 plus E3 d by dx3. Okay. I am just saying this is Ex, this is x, this is Ey, this is y, this is Ez, and this is z. Okay. So you will see that I am not going to write the term like this, I am going to write it like this. Okay. So what is del dot u? Ei d by dxi dotted with u is uj ej, right. That is, this is the del operator summed over 3 terms, this is the u vector summed over 3 terms, all the 3 components are there, you can have all 3 components, and because the index is repeated, it is summed over 3 terms. Okay. Again the same funda, this is going to contribute only if I is equal to j. If I is not equal to j, it is not going to contribute, okay, because of the orthogonality of the unit vectors. So basically this means I have to put I equal to j, I either put j equal to y or I equal to j, it does not matter. So this is equal to d by dxi of, I am putting j equal to y, ui, and this is your du by dx plus dv by dy plus dw by dz, which is what you are normally used to thinking. In the x component it is u, in the y component it is in the y direction it is v, in the z direction it is w, okay. So rather than write it like this, I am writing it like this, 1 is x direction, 2 is the y direction, so u2 is v, and whatever, third direction is w, okay. So you will see people, see when you read books, papers, somebody will say equation of continuity is dui dxi equal to 0. So you realize that he is using the Einstein summation convention and he is doing this, okay. So this is the equation of continuity. Look at gradient of f, how do you calculate that? This f is a scalar now, earlier del dot u was a vector, here f is a scalar, okay. So gradient operator is ei d by dxi, and f is a scalar, so there is no component, no fj ej business, f is a scalar function, it is not a vector. So this is nothing but ei df by dxi. Now the gradient has 3 components in the x, y and z direction, okay, and that the gradient is a vector. So that is being taken care of by this unit vector, and each component is the derivative in the x, first component is derivative with respect to x, second component is derivative with respect to y, third component is derivative with respect to z, okay. Supposing you want to calculate del squared f, I mean when you are dealing with partial differential equations, second order partial differential equations, you will have this Laplacian operator, okay. This is the Laplacian. This is, how is this defined? Divergence of gradient of f. Gradient of f is a vector, del is also a vector. So del dot del f is gradient is ej d by dxj, that is my operator, and this is ei df by dxi. What have I done? Del f which I already found out, I have put it here, and the gradient operator which I already by definition is ej d by dxj. Again I am using different indices to take into account all possible combinations, okay. So this is what I get. Here again this dot product makes sense only if I equal to j. If I is not equal to j, it is 0. So can you spend half a minute and tell me how this, what this simplifies to? I am going to do it. This is going to simplify to d square f by dxi squared. Okay, this is going to simplify to, because this is going to contribute only to if I is equal to j, okay. If I is not equal to j, 0, so that does not contribute. But I want to add a small point here. This is true only for rectangular coordinates. One has to be careful because what can happen is in other coordinate systems like the cylindrical coordinate system and the spherical coordinate system, when you vary one of the variables, one of the independent variables, theta for example in cylindrical coordinates, the unit vector itself can change. So, this is actually you have to treat it as derivative of a product of two things. Okay. In the rectangular Cartesian coordinates, if I vary x, the directions of Ex, Ey, Ez do not change, they are fixed. Okay. The directions of the unit vectors do not change when you go from one point to another point. When you are talking about other coordinate systems, the direction of the unit vector can change. Okay. And because the direction of the unit vector can change, you have to take into account how does the unit vector change with the coordinate. Okay. So, otherwise because this direction does not change, this derivative does not contribute. The this is like the derivative of a product of two variables or a product of two functions. Okay. You have to use the product rule for the differentiation. It turns out E1, E2, E3 do not change. So, it is like a constant, it comes out for rectangular Cartesian coordinates. So, for rectangular Cartesian coordinates, E1, E2, E3 can be treated as a constant with respect to space. So, I can take it out and only I am worried about Ei dot Ej. Okay. That is the important thing for you to remember, because sometimes you can't blindly take this as your del square. This is true only for rectangular coordinates. Okay. So, del square f is d square f by d xi squared. Again I is repeated because xi squared dxi dxi. Okay. This is d square f by dx squared plus d square f by dy squared plus d square f by dz squared. Okay. Yeah, that is right, because this is xi squared derivative, remember d by dxi, d by dxi or d by dxi. So, I is repeated. Point is, what I am trying to make is, in rectangular Cartesian coordinates, Ei do not change with x, y and z. So, if this is my x direction, the unit vector in this direction is always the same. Okay, it is parallel to the x axis, remember. Okay. So, basically what I am saying is d by dxi of Ei or Ej is 0, because the unit vector does not change. So, I am treating the Ej as a constant as far as this variable is concerned, and that is the reason I can pull it out of my derivative sign. So, okay. So, basically yeah, that Ei is like a constant. Okay. So, when I look at this particular term, when I look at this term d by dxj of Ei df by dxi, what I have written here, d by dxj, yeah. The derivative of two things are here, I will use the product rule. I am treating Ej as a constant, Ei as a constant, and I can take it out. Okay. So this is the same as saying Ej dotted with Ei d by d xj of df by dxi, because the unit vector does not change with the spatial coordinates. Okay. This is only because, I mean, Ei dotted, yeah, Ej dotted Ei, this thing, I can take the Ei out of this because they are like a product rule of differentiation. Okay. And this is a constant as far as this variable is concerned. Now, to explain a situation where this is not happening, consider the cylindrical coordinate system. Okay. Here, and we will just keep life simple, we just look at this as r direction and this as the theta direction. Okay. So, E theta is the unit vector in the theta direction, ER is the unit vector in the r direction. Okay. This is ER and this is in the theta direction, this is E theta. So, ER and E theta are the unit vectors in the r and theta directions. Now, as you change theta, so this is ER, and if you go, if you change theta, this is the ER at a different, this is the ER at theta equal to 0, this is the ER at some other theta, because the ER is pointing in the radial direction. Okay. At this theta, this is at theta equal to 0, and let us say this is at theta equal to some alpha, this is alpha. Clearly, the ER at alpha is different from the ER at 0, because ER is unit vector, it is decided both by the magnitude as well as the direction. The direction of ER is 0. I mean, the direction of ER is different from at theta equal to alpha and at theta equal to 0. Okay. So, direction of ER changes with theta. Here it is radially outward, here it is also radially outward, but at theta. So, with theta, change in theta, ER is different. Okay. So, all I am saying is dER by d theta is not equal to 0. So, when I am doing my product rule for the differentiation, you need to be careful, okay, about this fact. Similarly, E theta also changes, this is E theta. Here it is perpendicular to this, right, this is the theta direction, E theta. Here E theta is in this direction. So, here also d by d theta of E theta is not equal to 0. We will see that, I will discuss this again in detail. All I am trying to tell you is, you need to be aware of what you are doing when you are doing these identities, okay. And it is not that you can just lay out and apply some formula and get something, because then you will be missing out some extra terms, and those terms are crucial, okay. So, when you go to cylindrical coordinates or spherical coordinates in the Navier-Stokes equation, you will get some extra terms, so that is coming because of this, because of the contributions from these terms which are not 0, okay. And we will do these examples and then it will become clear. We started with motivating this whole thing by saying we have to look at that del dot rho v term, right. So, let us go back to the del dot rho v term which came in your Navier-Stokes equations. How do you find this? That is the question, okay. We will try and apply whatever we have done so far to evaluate this term. okay. So, I am going to write del as, and again whatever I am doing is only for Cartesian coordinates, okay. So, I am going to say for rectangular Cartesian coordinates, I am going to write del as E by I d by dxi, and this is dotted with rho, and V I will write as Vj Ej, and the other V I will write as Vk Ek, okay. Vk Ek is also summing over 3 terms, Vj Ej is also summing over 3 terms, but I do not use the same index to keep things as general as possible, to allow for all possible combinations of I, j, k which I have to consider in my calculation, okay. If you assume I is equal to j to begin with, then there is no fun, then you definitely not only is no fun, you are going to get a wrong result, okay. So, now there are 2 unit vectors on the right hand side of the dot here for the dot product which we derived in the Navier-Stokes, and this is the term of the del operator, the dot 2 unit vectors. So, how do you go about evaluating this? You go about evaluating this by considering the dot between the 2 unit vectors which are adjacent to the dot. The unit vector adjacent on the left hand side is Ei, the unit vector adjacent on the right hand side is Ej, okay. So, you consider only these 2 vectors Ei and Ej, you forget about this guy, this is not adjacent, this guy is adjacent, this guy is the one which is right to the right, okay, that guy is right, okay. So, now we do not worry about that. So, only these 2 you have to dot, that means when you dot these 2, what do I get? Ei dot Ej is delta Ij, I only consider I equal to j, okay. So, I get Ei dotted Ej is I equal to j, so I get d by dxi of rho I Vi Vk Ek, this is my term, okay. This is equal to this. So, basically when you have a dot product, so consider the 2 unit vectors which are adjacent to the dot, okay, and then proceed. That is what I have done. So, now how do I expand this out? D by dxi of rho Vi Vk Ek. Totally how many terms will be here? 9 terms, because I is repeated 3 from 1 to 3 and j is repeated from 1 to 3. I have to look at all the possible combinations. For example, I can fix k as 1, okay, and then sum over I get 3 terms. Fix k as 2, sum over 3 terms, I get 3 more terms. Fix k as 3 and sum over 3 terms, I get 9 terms, okay. So, this is basically 9 terms. What I want to do is now remember the origin of this. How did this term come? From my momentum balance equation, right, and therefore this is a momentum, so it is a vector. So, when I take E1, I am going to be looking at the x momentum. When I take E2, I look at the y momentum. When I take E3, I look at the z momentum, okay. So, E1, so k equal to 1 implies x momentum balance, because that is the one I am going to x direction moment vector is what I am going to get. K equal to 2 is y momentum balance and k equal to 3 is the z momentum balance. Okay. So, I am going to fix k equal to 1 and try and solve this. So, I am fixing k as 1 because when I am actually solving, see, this particular equation is completely useless because it is a nice compact representation, but when I actually have to solve the problem, I have to write the equations in the x, y, z direction like we did for the stratified flow problem and then simplify. I mean, that is how you go about solving, right. So, you have to write the equations in each direction and then solve. So, that is what we are going to do now. So, although this x term is great, but you need to know how to write it in each direction. So, now I have for k equal to 1, that is the x momentum balance, I have d by d xi of rho vi v1. Okay, because I am fixing k equal to 1, this becomes an E1 of course. Okay, k is 1, E1, V1, and now because this is fixed, I am looking only at the x direction. Okay, that is fixed. I put I into summation. If it is 1, it is just V1, E1. Okay, what do I get here? I am going to sum over these guys. So, d by dxi, d by dx1, rho V1, V1. Okay, plus d by dx2 rho V2 V1 plus d by dx3 rho V3 V1, and this is where does the E1 go? E1 I am not writing because it is in the x direction. So, there is an E1 because I am going to write the momentum balance for x direction, y direction, z direction. So, this is in the x direction, I already know that. This is E1 x direction. Okay. So, again this is a derivative, I am using product rule. Okay. Because it is Cartesian coordinates, I do not worry about the derivative of E with respect to x, otherwise I have to worry about that. I have to worry about how does the unit vector change with my coordinate. Okay. So, I do not worry about how the unit vector changes the coordinate because in Cartesian coordinates it does not change. So, it is a constant, I take it outside. Okay. And then I will use the product rule, all I have done is written the summation, and this is basically your and there is a row somewhere, row is here. Okay. So, this is how I would go about evaluating it, but this is a form which I will use for making my calculations. When I make my calculations to find the velocity flow field, I need to write my x momentum equation, y momentum equation, z momentum equation, simplify and then calculate. Okay. This particular equation, divergence of rho VV, if I tell you, is great, it is correct, but I can't use it for calculating. Okay. So, now one thing, how can I want to use the product rule here, okay, and expand this. So, what do I get? You would get d by, how are we doing? I think we will stop. Basically, what is going to happen, I want you to do this. Use the product rule you will see that 3 terms will disappear because of continuity, okay. The totally each is going to give rise to, you can take rho to be constant, incompressible. Each of these terms will give rise to 2 terms because of product rule, and then you will see because of continuity 3 terms will drop off, okay. Only 3 terms will remain. So, we will do that in the next class, but I want you to do it before the next class.